I didn't record Wednesday's pre-lab, but I will record today just in case you have a couple people out. Okay, so I want to go over two things today. First, I want to revisit a flame lab because it ties in directly to what we talked about on Wednesday and what you did on Thursday. Did everybody get through the lab assignment yesterday? You did get through it? Yes. Was it helpful? Awesome. Okay, we got a couple shaking heads. So the reason if y'all all have your computers, I want to go back. I'll go to this slide. I'm going to revisit this flame lab really quickly because I think that there was the very last page. Some of y'all were a little confused about the very last page of the flame lab. So I didn't make it due last night. I made it due tomorrow. No, I made it due at midnight tonight. So the flame lab from last week is due at midnight tonight because I want you to be able to revisit this last page. So this last page of the flame lab, if you want to go ahead, of the, what's it called? The last page of the flame lab asks you to write the electron configuration and the abbreviated orbital diagram for these 7 compounds. Okay, and if you go to the gizmos that I gave you on Wednesday, the electron configuration, this here is the electron configuration. It looks like 1s2, 2s2, 2p1 for boron. And this up top, these boxes with arrows, that is the orbital diagram. So some of you wrote the electron configuration twice. Some of you, a handful of you got it right. Only like 8 of you have already turned it in, so I kind of looked at those. So if you, I brought a new, in case you were wrong, I've got a new printout of just this last page of the flame lab. Beautiful. Okay, you're good to go, but you haven't quite finished yet. So, so I want you to open gizmos and then open the last page of your flame lab or this new one and figure out, yeah. So we got like 10 minutes. We'll work on So the orbital diagram is these boxes. So arrows. Yeah. Okay, so so that is called the noble gas configuration. Yeah. So, okay, you got a pencil again. What new one? Okay. Oh no. Okay. Awesome. Perfect. Okay, cool. But I just wanted y'all to be able to see that they map directly onto each other. Okay. So this is the noble gas configuration. So if you want a new sheet, you can do a new sheet, or you can just cross that out and do it. Oh, got it.
Okay, so even if I submit this, can I just do a second check?
Yeah, you can resubmit a new one. Yes. Yes.
So is this wrong?
This is great. Yours is perfect. Awesome. Yours looks like hers is good. If not, I got it. So the abbreviated. Okay. So I wrote it very small right here. Sorry. So the away for this example for boron, the full electron configuration involves everything. With the abbreviated configuration, for either one, it's the noble gas configuration. So you look in the periodic table, go to the last noble gas, that far right column, and you put that in brackets. So helium can replace 1s2. Helium in brackets. So it'd be helium in brackets, and then the 2s box and the 2p box would be boron. I think I have one more example. So for selenium, I've got 2 examples. You've got 7 to do. With selenium, we go all the way to the 4th shell. It's in the 4th row. So its full electron configuration is written right here. To do the abbreviated, you can replace 1s2 to 3p6 with AR in brackets. And you can do the same thing for the orbital diagram. You can replace everything from 1s to 3p6 with argon brackets. That's the abbreviation, which that's why y'all, I think that's why y'all were confused, because you know that the noble gas configuration is a shorthand for the electron configuration, but it wants the boxes. This is the orbital diagram. Does that make sense? So you're right, if you were writing noble gas configuration, that first part is right. Correct. Yeah, so the NE is right, it's just this should be boxes with arrows. Where did I do? You want a new one? Yeah, beautiful, this is perfect. And you remember to circle the valence like this. You want a new one, are you good? Okay. It's just a back page. So if you wrote boxes with arrows in it.
Wow, Marcus.
This is a week ago. Yeah.
That's how we're gonna start. I bet. No, I bet.
I did my right.
You did yours right?
Yes.
No, that's.
I finished where.
Yeah, I know, that's right. You got it? Okay.
I did put the little gas configuration.
That's okay.
So this is.
Yeah. Okay. Okay, you're happy with it. And you're good. So yeah, so the orbital diagram. And so, okay. Yeah, so let me go back to the easier one. So the abbreviated orbital diagram for boron. Boron's in the second row, so it would be helium in brackets. And then 2 for the 2s. Yeah, so that would be abbreviated for boron. We don't have to write all the 1s's because we have that summarized with the helium. And write 2s, 2p.
Wait, for all the gizmos of the element builder?
No, this is the periodic table builder. No, it's the periodic electron configuration. So electron configurations, click launch, and then click that tab, electron configuration tab. Yeah, and so you start adding it, you click the next element to get to, there you go. Yes. So D is not in a valence electron. Okay. Which one are you on? N? Okay, that's good. Let's go. Okay, so when it comes to circling the valence electrons, so this is 10. It has 10 is in SN. Sorry, it's SN, not TN. I always want to write SN. So 10 is in the 5th row. And if you count all of its electrons, it has 2 in the 5s, so that's the outer row. But then where do the 4d electrons go? Do they go in the outer shell or do they go in the fourth shell? They go in the fourth shell. So the d electrons are one orbital below the s orbital. There's 10. And then the p goes in the, it's in the fifth as well. So how many p electrons does it have? 10, 2. So it only has 4 electrons in the outer shell, the 4s2 and the 4p2. The 3d10 are in the third shell. They're not in the outer shell. They're not valence electrons. There can only, how many valence electrons can there be? 8. There's a octet rule that we talked about, but basically the S and the P electrons are in the outer shell. The D and the F are inside. Remember, because it's like first row, 1s, second row, 2s, third row, 3s, fourth row, 4s, 3d. That 3d means it's in the third shell, not the fourth. So there will, when you're circling the valence electrons, you'll only circle the S and the P. And if you go, so this is it. So if you'll notice when you get, the further you get out on this Gizmos lab, they start hiding the inner electrons, are called inner electrons. And how many electrons? 1, 2, 3, 4, 5, 6 are in the valence shell. It has 4s2 and 4p4. The 3d10 are not in the valence shell. That's why I like this. I went home on Wednesday thinking maybe y'all didn't actually look at this one. This is like super helpful for understanding these really complex ideas because it lays it out for you in visual terms and you can test every single, it has every single atom on the periodic table in there. And then there's one more way you can check your answers. Does everybody remember this periodic table that I gave you, the black and white one?
Yeah.
In incredibly tiny font, it has the noble gas electron configuration written down for you. So you should be able to use the periodic table to write it out, and then you can go check your answer with this periodic table. So you should, every single one of you should get every one of these answers correct, because you have the answer for you right here. Yeah, I know, these resources are useful. Does anybody need a new periodic table? Have they lost yours? Or do you want one right now?
Is this what we're gonna be doing?
We got one more part today. We're gonna get back to talking about ions. But I wanted y'all, I've seen a bunch of blank pages. So I wanted y'all to know that these answers are out there if you are confused. Yeah. Well, looking good, looking good. Sort of. Okay, yeah. Just put the arrows with boxes around them. You can leave the NE there, and instead of this 2s23p5, you're gonna have a box labeled 2s2 with 2 arrows, 3 boxes labeled 2p with how many arrows? Yeah. That's the preferred way to do it. Yes, because they have opposite spin. Yes. All good. Oh yeah, looking good. Looking good. You're working on the SNLs. You're good. Okay, awesome. Good on it. Got the top and right. You understand how to get the overlay? Awesome. Your mom has your up down there. Yes. She wants to. Okay. Okay, so do I.
So it feels like that's cool.
Yes. What? That's why I gave you a new sheet, so if you run out and if you did the orbital diagram, then you're good. Not writing. But if you just like wrote the 1s2, if it's the second one. Yeah, you can just add the bottom. That's just worth it. Yeah, you can on this and then submit that one page with your, yeah, exactly.
Not just chilling in
That one
is correct.
Okay.
Yeah. The only one more thing you have to do is circle the base.
That's so weird.
Okay. Awesome. Okay, y'all ready to go back to the lecture? Okay. Let me make sure there's nothing else here. Oh, okay. I have a couple of reminders before you turn in your homework, before you turn in the lab report. Okay. So the complete electron configuration always starts with 1s. You kind of always start like at the top of the periodic table. So for hydrogen, it's going to be 1s1. For helium, 1s2. For lithium, 1s2, 2s1. The orbital diagram are these boxes with arrows. And it asks, there's one more part of the question that it asked is to circle the valence electron. So what I just said, our valence electrons are always going to be the electrons in the s and the p orbitals, not the d. So you could circle like this on the orbital diagram, or you could circle like this or like this on the electron configuration. Cool. Yeah, electrons in the d and f orbitals are not valence electrons. They are one shell inside. Valence means outer shell. So it's different as you go down the row, which one is a valence shell, but the valence means outer shell. Yes. That's just part of the question. Just because it said to. I think that's to make sure that you know what a valence electron is. It's just for educational purposes. Yes. Because basically when we're talking about ions, which we're going to do in 1 minute here, the electrons that get shared are in the valence electron. They're not like this. These electrons here in the first and second shell are not going to go to another element. It's only these that can be shared with another element. Excellent question. Any other questions about this flame lab before we go on? Okay. Okay, so I want to go back to chapter 3, the ionic compounds. Okay, y'all want to do something not chemistry for 1 second? Okay, I also teach yoga. We do a lot of breath work in yoga. Okay, so let's just we'll take 3 breaths together, okay? As soon as everybody stops and quiets down, we'll do it together, okay? Okay, we'll take 1 deep inhale and a deep exhale. The deep inhale, lift your shoulders with your ears. And exhale, drop them down. Okay, 1 more deep inhale. Okay. I don't know if that's calming or not. Usually, like a little bit more breath work every day is good for you. It's good we are working our brains all day long, but our breath is like the life force in us. So if you're ever stressed out, you can focus on your breath. Remember that we're all here. Okay, so I want to go back to chapter 3, we'll finish this today. We're actually going to save a part of it until next week because I think it makes a little bit more sense. Next week, we're going to talk about covalent bonds, but today we're going to finish with ionic bonds and ionic compounds. Okay, so we had this, we used gizmos. Yesterday, this is a screenshot from the ionic bond gizmo application. This is an example of sodium chloride. Sodium has a +1 charge, and the chlorine has a -1 charge because sodium gave an electron to chlorine. And then we went over some ionic compounds have more than one metal or more than one nonmetal. So what's the molecular formula of beryllium and chloride? BeCl2. So for every one beryllium ion, there is 2 chlorine ions. Okay, and so when we make compounds, so if we, that far left, the second to the last column in the periodic table is fluorine, chlorine, bromine, iodine. And all of these tend to form ions with a -1 charge. But their ion, it's written as with the minus charge, the symbol with the minus charge, but they have a name change. So it's called a fluoride, chloride, bromide, iodide. So that INE changes to an IDE. And that's how you know it's an ion. We also, on the far left of the column, we have a lot of, what are things with a positive charge called? What are those ions called? Cations. So, but if you look, are all of these, do they have more than one ion possible? Yes. So we played with copper in the flame lab. Copper can be +1 or +2. Does anybody have any idea how that could happen? It's got, so copper, what row is copper in? Copper, Cu, it's in the 4th row. Okay, so copper is in the 4th row. So it's 1, 2, 3, 4 shells. And so if we write the electron gas, if we write the electron configuration for copper, if we start with the 4s, it has 2 in the 4s. And then how many 3d electrons does it have? One less than 10. 9. So you would write 9 electrons on that 3rd shell. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's, if you're counting across the periodic table, that's what it says. But if you get out your periodic table and or if you use gizmos to do that orbital diagram, what does it say is how many electrons in the 4s orbital are there according to your periodic table? Yeah, so the way we wrote it, there's 2 and 9. But it actually, instead of having 2 outside, it likes to have the 3D full and just 1 in 4s. So copper, its electron configuration is 4s1 3d10.
When you're looking at it with the +1, the +2, the +2,
That means those are the possible ions. Okay, so copper, unlike our prediction, unlike most things, So most things usually we fill that 4s too. We fill the 4s before you do fill anything else. But actually one of these electrons goes into the D shell. So this is the configuration for copper. So if copper loses one electron in this S shell, it can become copper plus 1. And then it can also lose an electron from this inner shell to be copper plus 2. Okay, so these transition metals, one of the reasons why they're called transition metals, is their electrons can transition between orbitals in a way that like the non-metals cannot. So that's a little confusing, but again, it's written on your periodic table. So if you notice, like all of these, so magnesium can form plus 2, plus 3, plus 4, plus 5, plus 6. It can get rid of lots of electrons. The first column, they can only be plus 1. The second column, they can only be plus 2. But a lot of these transmissions, they have multiple ion configurations because they can give away ion electrons from their S shell and from their inner P shell. Okay, so I wrote that here on this slide. So copper has a neutral configuration with 10 in the 3D and 1 in the 4s. Copper plus gets rid of its 4s1. Copper 2 plus gets rid of the 4s1 and one of its D electrons. Does that make sense? Is anybody confused? Awesome.
So, are these why they transition metals? Because of why they can change their electrons. Their charges.
They have, so because their second outermost shell has so many electrons in it,
Yeah.
this charge isn't as strong on the outside, so these can leave. But also, it's like, you remember when Mr. Thomas was talking about like having fun at a concert, you know, you're like, okay, maybe I want to go up for a better seat with better view, but then you're like, my friends are down there, and they go back down there. So these electrons can move around to their orbitals. They're a little bit more flexible because this attraction of the nucleus is a little bit less because there's so many electrons in that second to last shell.
So the second to last shell, those are the ones that can move back and forth.
That's typically the ones that are moving, yes. You kind of can't really, these are pretty stuck. They're really close to this nucleus with the charges. So if we go back, but pretty much all of these, if you look for all of these, chromium is in the D block. Copper's in the D block. Iron is in the D block. So all of these transition metals, they can have multiple ion configurations. And then the way that we name them is typically by adding a Roman numeral in their name. So copper 2 ion, copper 1 ion. That lets you know exactly what the charge is. Okay, so 10. So 10 is it's in the 5th row. Okay, so 10, it has 2, 4, 10, 5s electron, 2, 5s electrons, and 2, 5p.
Says 4, 5.
Oh, okay. So it has 4 electrons in its outermost shell. 2 of them are 2s and 2p. So you can see 2p's. So sorry. This might be. Oh, that's still copper. Sorry, I didn't put 10 there. It has 2p electrons and 2s electrons. So it can lose both of its 2p electrons and become SN2+, or it can lose all 4 of its valence electrons and become SN4+. So you don't have to memorize all of these, but it's good to know the logic. So here, if we go look at it for SN, it says it can form a 2+ and a +2 and a +4. But it's always losing the valence electrons. Okay, do you remember talking about ionization energy on Monday? A little bit. It was part of the gizmos that y'all did on Thursday. So these were 2 different charts for the ionization energy. And carbon is right here. Carbon has a pretty high ionization energy. It never forms ions, but the other things in that same row, same group with carbon can lose their electrons. And so that's written here, and it has to do with their ionization energy. So carbon, all of its electrons are very close to the nucleus. It's not going to lose their electrons. But the things lower down, once you've got all these d electrons that are shielding the nucleus, their electrons can leave to form ions. They have a lower ionization energy. Okay, so you don't, like I said, you don't have to memorize all these numbers. They're given to you in various periodic tables, which ones are likely to form ions and which ions are likely to form. So please hold on to your periodic table and refer to it for all your quiz and homework questions. Okay, one more thing and then I'm going to give you a little handout. So ions can have a positive or a negative charge. And so the way we did this a little bit yesterday with some of the ionic compounds that form. Some of them are easy. NaCl doesn't have any subscripts. Na has a +1, Cl has a -1, they form NaCl. If they have more than a +1 or -1 charge, when you bring 2 elements together that have a different charge, that don't cancel out perfectly, this subscript right here, Al +3, this 3 goes over to the oxygen, this 2 goes over to the aluminum, and we get aluminum 2, oxygen 3.
Plus means it wants to take, right? And minus it wants to give, it want to give.
Plus means it has already given away 2.
Okay. So yeah, with aluminum +3, it's already giving away.
Yes, so aluminum wants to give 3 electrons to oxygen. Oxygen can actually only take 2. So you have to use multiple atoms together. So 2 aluminum atoms give 3 electrons to 3 oxygen atoms. So that's 3 times 2 is 6, and 2 times 3 is 6. So they're trading 6 electrons. Okay, so I have a practice for you today. Okay, so I've given you, this is like 10 compounds. Yeah. Just fill in the blanks using the 3 examples you've been given.
I don't know.
All right. Okay. I would do this first. Yeah. Tell you guys again, you're on the next one. You're on which one is not first.
Oh no, you have to do that on Ionic stuff. It's just fluoride.
Yeah.
Would it be just fluoride or would it
It's two.
Yes, you are correct. You have to change it for.
Yeah. Oh, we got it. Yeah. Oh, yeah. And then give us a question.
Okay. Okay, we're gonna, yeah, we're gonna go over that on Monday. Yeah, okay. Yeah.
Potassium, would it be potassium?
Yeah, no, these are all, yeah, there was one. Oh.
Can you guys please be quiet so you can hear what she said? Okay.
Yes, beautiful. I'm pretty sure it's free. Yeah, it's free. So because it should be, yeah, I think you just push a button on it. Woo! Nice. No.
What grade was it? What grade was it? What grade was it?
Nope, there's no, we're not there yet. We will, next week, when we talk about like the seeds, like you're thinking like carbon dioxide, like, but that's a different kind of phosphorus than next week. She's all excited. There is a quiz in like.
Oh, okay.
You want me to look at your work, so they just get it right, or you get it wrong on the quiz. That's for you to see if you know this, before you get it wrong on the quiz. Got it? Nope. Then just send me it. Yeah, awesome.
This is for calcium, calcium, so it's minus
3 calciums and how many nitrogens? Well, it's 2 times, so you got 2 and 3 here, so you need 2 and 3 there. Yes.
calcium.
Yep, that one's good, that one's good. Okay. Yes, awesome. Again. Okay, cool, you are correct. I didn't mean to write that, because we haven't quite gotten there yet, but yes. Yes. It's, I didn't write phosphorus. Yeah.
Wait, it says you use phosphorus.
I meant for you to use phosphorus, but if you can use phosphate, you can. Since I learned that you have to, since you know these. Make you feel for negative. Yeah. You're running a big result.
So it's 1,000.
So if this was possible, Russ, it would be possible. Because it's possible.
Yeah, we keep using the side area.
Yay.
I had a kid at the speed of light.
That already.
Okay, no, we're gonna do a little more. Okay, so what was compound that's produced from tin, fluoride, tin, 2, and chlorine?
SNF.
SNF2, correct? What is potassium and bromine? What does that make?
KBR.
KBr, awesome. Does anybody have any questions about that handout? You're not done yet? Okay. Okay, so if you go on to Canvas, there is a quiz called Electrons and Ions. It's based off of everything we covered this week. And it's worth 10 points, and it's due Sunday. But you have 15 minutes to work on it right now.